Here, though, we can notice that there are two negative charges. So for the first phosphoric acid group, we have one negative charge on one oxygen. For the second one, we have only one negative charge. But for the last one, we have two negative charges. So this phosphoric acid group is relatively more unstable than the first two, and so in order for it to be broken, it will be easier, and if it's easier, it will produce less energy because the compound is already rejecting it, doesn't really want it to be there relative to the other two ones. So the macroergic bonds that are going to be broken are these bonds right there, and we refer to them with a squiggle like that. So in order to break the phosphoric acid groups, sometimes one of them are just broken and other times both of them are broken, and this is done through hydrolysis. So by adding water, we could lose one bond, and throughout the first step, so delta G1, there's a release of 7.3 kilocalories per mole. If the second bond is broken, there is a release of -8, so delta G2 kilocalories per mole. So we can say that if ATP, adenosine triphosphate, is hydrolyzed into ADP, which is adenosine diphosphate, because we would have two phosphate groups, plus PI, which is the lone phosphorus group or phosphoric acid group that would be removed, this reaction would release that amount of energy. While if ATP is hydrolyzed into AMP, AMP is adenosine monophosphate plus two phosphorus groups bound to each other. These two phosphorus groups bound to each other will break down in order to give two PIs. So this reaction would give the -8, and the total reaction, so this part is -8 kilocalories, and this one is just like the first one, -7.3 kilocalories per mole. The total reaction of changing ATP into AMP plus 2 PIs gives us -15.3 kilocalories. So obviously we would use the first reaction to supply energy for reactions that need less than 7.3 kilocalories. But if the reaction needs more and more energy, the ATP would actually be cleaved, or it would change into AMP. And this is the idea of how adenosine triphosphate is broken down in order to give energy for the compounds, in order to make this indirect energy coupling thing. So this is our lesson for today. I hope it was easy and clear. Just understanding the concept of how macroergic compounds work is very important, and it makes understanding the metabolic activity It makes it much easier. Next time we're gonna talk about more examples in which macroergic compounds are involved, different macroergic compounds other than adenosine triphosphate, and this would let us get more involved in the metabolic process, and it will be an introduction before we start talking about glycolysis. So until the next time, I thank you for watching and see you.